In this video, we'll get to discuss one of the most important results in this course, Stokes' theorem, which can be regarded as a higher dimensional version of Green's theorem. And whereas Green's theorem related a double integral over a plane region to a line integral around the boundary curve of that region, Stokes' theorem will relate a surface integral over some surface to the line integral around the boundary curve of that surface, which curve is generally a space curve. So to help you imagine this, let me illustrate what I just said. So we have a surface, a two-dimensional surface sitting in space in our 3D coordinate system. So this surface, let's call this S, and it has a boundary curve. So it has the boundary, which may be this curve. Let's call this C, this boundary curve. And as soon as we give this surface an orientation, meaning that we choose the direction of normal vectors on the points of the surface, we will have a direction for the curve, the boundary curve, induced in the following way. You imagine that you stand on that boundary curve with your head pointing in the direction of the normal vectors, and you want to walk along that curve so that you always have the surface on your left side. And in this case, the way to do that is to walk that way, in that direction. So this will be the positive direction for our boundary curve C. Okay, so with this setup, we are ready to state Stokes' theorem, which says that if you have a vector field whose components have continuous partial derivatives. So imagine you have this vector field F defined in space, in a region of space which includes this surface and its boundary in it. It has components P, Q, and R, which are functions of x, y, and z, and we assume that P, Q, and R have continuous partial derivatives with respect to x, y, and z. Then the following relation holds true. The line integral of F, the vector field F, around that closed curve C will be equal to the surface integral of the curl of F across that surface S. So this is Stokes' theorem, and it's one of the most important results or theorems in vector calculus. So to clarify, or to make it even more clear, what we have on the left-hand side is the integral of the tangential component of F around that curve C, and on the right-hand side we have the normal component of the curl of F being integrated across that surface S. And the claim is that these two integrals give you the same result. Sometimes people use the symbol del S to denote that the boundary of S is the curve C. So that is something you might see in certain sources. And there is a clear analogy between Stokes' theorem and the fundamental theorem of calculus. Because just like with the fundamental theorem of calculus, we have a sort of derivative of a function of on one side being integrated, and on the other side we have that function, only the value of that function taken at the boundary of that region over which we integrate. And as I said, Stokes' theorem is a generalization of Green's theorem, because if that surface lies flat in the xy plane and its orientation is so that the normal vectors point upward. So and then we have the unit vector k as the normal vector at every point on that region, that surface, flat surface. Then the right hand side will become exactly that dq over dx minus dp over dy being integrated over that region that is the flat surface. And that's what we had in Green's theorem, and the left hand side is identical, it's just the line integral of our vector field, which now would have only two components because we assume that it lies in the plane. So this is precisely why Stokes' theorem is a generalization of Green's theorem. So let's see an example. Here is the following question or task: to evaluate the line integral of a vector function f of x, y, and z with components minus y squared, x, and z squared along a curve that is the intersection of a cylinder with a plane. So the cylinder has the equation x squared plus y squared equals 1, and the plane has the equation y plus z equals 2. With the intersection we get this ellipse, and it has a certain orientation, and that's what we want to integrate the vector field along. And the way I would like you to evaluate this line integral is to use Stokes' theorem. So set up everything you need on the right hand side of Stokes' theorem and evaluate that surface integral to find the line integral of f. So pause the video and input your answer below. Okay, I hope you paused it and have found that this line integral will be equal to pi, and it's because of the following reason. So we want to apply Stokes' theorem to compute, we would compute the curl of f, the surface integral of the curl of f across that surface S, which let me just quickly sketch over here. What we had is a cylinder of radius 1 with axis, with its axis being the z-axis, and we intersected that cylinder by a plane. So cut it like that, or something like that. So our surface is now, that is the top of that cut, and the boundary curve is that ellipse that we have there. So that's C. Okay, so what we need first is the curl of f. So let's compute that first. So remember that f had the components minus y squared, x, and z squared. So if we want to find the curl, we can use the usual definition. So for the curl of f, can just evaluate the following 3 by 3 determinant with I, j, and k, these basis vectors in the first row, the partial derivatives with respect to x, y, and z in the second row, and the components of f in the third row. So if you evaluate this determinant, you will find that the I and j components of the curl of f vanish, and it's only the k component that is not 0. And for the k component, you find that it's the derivative of x with respect to x, so that's 1, minus the derivative of minus y squared with respect to y, so that's minus 2y, but you have to subtract that, so that's plus 2y, and that's the k component, the only component that does not vanish for this curl. So that's the curl. As for the normal vector, because remember what it means to evaluate this surface integral is we have to take the normal vector, so the curl of f dotted with the normal vector, and then we evaluate that surface integral. So what's that normal vector? For that, we just have to realize that this surface is just the intersection of the plane with the equation x, y plus z equals 2, and the cylinder x squared plus y squared equals 1. So, but it is a piece of that plane y plus z equals 2, and for that plane, the plane itself we could parameterize by the following vector function. So that's for the plane. It could be parameterized as I times x times I, y times j, and for the z component we have to solve this equation for z, which is just z equals 2 minus y. Differentiating this vector function with respect to x and y will give us, well, for the x derivative we'll get I. For the y derivative, so r sub y, we will obtain j minus k. So what we need to find the normal vector is the cross product of these two derivatives of r. So the cross product of I and j minus k will simply be, well, the cross product of I and j gives you k, and the cross product of I and minus k will give you j. So this is the normal vector that we have to use in this dot product. So let's compute the dot product now of the curl of f, which we have found to be 1 plus 2y times k, and the normal vector, which we have found to be k plus j. So it's 1 plus 2y times k dotted with k plus j. Well, the dot product of k with itself will give you 1 because it's a unit vector. K is a unit vector. And the dot product of k and j will give you 0 because these two vectors are perpendicular to each other. So we will simply get 1 plus 2 I for this dot product. 1 plus 2y for this dot product. And that is what we have to integrate. And we can integrate that function along that surface. So how do we do that? We can use cylindrical coordinates and realize that basically what we have there is that surface is the piece of the plane y plus z equals 2 that sits above the unit disk. In the xy plane we have the unit disk, and above it sits that surface S contained in the plane y plus z equals 2. So for that we can use cylindrical coordinates. So cylindrical coordinates can be used, and basically we can find that what we are doing is computing the surface integral of this function. So, and now we can use cylindrical coordinates. Where we have x be r times the cosine of theta, y be r times the sine of theta, and z is of course equals to z, but it's also equal to 2 minus y in that plane. But the important thing here is y, because we have 1 plus 2y appearing in that integral. We have to set up the boundaries for r and theta. So r changes between 0 and 1 because we look at that unit disk where the distance from the z-axis goes from 0 to 1. And theta, our angle, our polar angle, can change anywhere between 0 and 2 pi. Okay, so with these compute this surface integral. So we have 1 plus twice y, which is r times the sine of theta. Okay, because we are using cylindrical coordinates, we have to account for the distortion in areas by having this Jacobian, this extra factor of r in there, and then we integrate with respect to r and with respect to theta. So this is the double integral that we need to evaluate. So let's do the inner integral first. So the antiderivative of that function, which is r plus 2r squared, the sine of theta, will be r squared over 2 plus 2r cubed over 3 times the cosine of, times the sine of theta, as r changes from 0 to 1. Then we integrate with respect to theta. At r equals 1, we get something that's not 0. Namely, it is 1 over 2 in the first term plus 2 over 3 times the sine of theta in the second term. And this is what we have to integrate with respect to theta. The antiderivative of this function is theta over 2 minus 2 over 3 times the cosine of theta as it changes from 0 to 2 pi. The term with the cosine will, of course, vanish, both at theta equals 2 pi and theta equals, but won't vanish, but will cancel each other. That's what I meant. So the cosine of 2 pi is 1, the cosine of 0 is also 1, so that term will cancel, and it's only the theta term that remains, and it's only at pi equals 2 pi that we get something that's not 0. We get 2 pi over 2, so that is pi, and this is the value of the line integral that we have to find. Okay, so I hope you enjoyed this video, and I'll see you in the next one.